Here's some discussion of radar data. This comes from our work with Kansas, where Kansas either typically flies on aircraft radar. Those radar observes the Earth, or it actually observes the North and South Pole, the ice. They observe the ice, and then they probe the ice and see the ice bed, and this allows them to provide the boundary conditions needed in models of the glaciers to study glacier and ice sheet dynamics. There's a picture here of an internet connection. Actually, the North Pole and South Pole do not have good internet connection. And so these are a pseudo Internet of Things, because typically the internet connection is done by taking the data from these sensors, putting them on disks, putting the disk on a plane, and running the plane back to the continental US, and then we can put it all on the internet. Here's some pictures of this is done by the UITS at IU. They built all this stuff. Here's the internet connection. Here is the cyber infrastructure used to process the data from these radar. And this is all packaged up before it's shipped to Greenland to do some measurements. These are all laptops and servers and disks and things like that. You get through a lot of disks in one of these field expeditions, because the disk is relatively tough exposure for the disks in this world. When we take all this data, we then do analytics on it. This work is done by Jerome Mitchell and David Crandall. There's more details of this in the radar informatics section of this course. You do things like is illustrated here. We take analytics method. Here's one based on some earlier work, which basically takes these pictures, which are the radar pictures from these sensors, and tries to find the layers. In this case here, this is the ice-air boundary, and this green, that's the red, and the green is the ice-rock boundary, where the bottom of the glacier is pretty rocky, the bottom of the glacier. And these are versions done by human beings, and here versions done by computers. And so here the data analytics is finding layers in images. So you get huge numbers of images, and you want to do image processing on them. At some crude level, that's what the pathology problem is. There you get lots of images representing where you try to scan for tumors, and that's again an image processing algorithm. It's important to note that when we have these sensors, we need to put them in the field. In the field, there are lots of issues like the amount of power being limited. And so it's interesting to look at the use of GPUs, which are more power efficient. And here's some plots of the speed up you get on a GPU. So rather than having several ordinary Intel CPUs, you do add a GPU and get more power, or I should say, get as much processing as you wanted, but at lower electrical power cost. So there's the types of things one wants to do in this area. Here's an example of another use of sensors here in observing the ocean, where you have lots of sensors and robots running around the seafloor, sending the data up, and the so-called Ocean Observatory Initiative has a cloud-based architecture for storing all this stuff, and then you analyze it on the Azure cloud and then send it back down to your computer. So this is just typical of many related applications of this type, because you don't just have sensors in the oceans, you have sensors in the forest, you have sensors in your cars, you have sensors in your homes, you have sensors in you, and all of those are going to go up into the cloud and get analyzed. Here is another related one for so-called remote sensing geoscience, where again they're taking more different imagery from lots of locations, processing the image to form complete pictures, and then these are natural types of pleasingly parallel application, because each image can be done separately, and they run very well on clouds, in this case the Azure cloud.